Hello everyone, my name is Rajesh Sharma. Good afternoon, and I am presenting my phase 1 work on estimating remaining useful life and state of health of EV batteries using hybrid physics informed framework. I am working under the mentorship of Dr. Sandeep Padare. So let's start with introduction and motivation. As we transition to electric vehicles, reliable battery diagnosis are essential. As we know, lithium-ion batteries degrades non-linearly, which leads to certain type of risk and challenges. See, first one is safety risk, where we overestimate the health, and we might overcharge the battery, which leads to some thermal issues. The second one is economic risk. If we underestimate the health, we retire good batteries too early, which leads to increase costs significantly. My objective is to build a lightweight framework that is safe, accurate, and simple enough to run on small chips or resource constrained battery management system (BMS). In literature survey, uh, I found two type of approaches is there. So first one is model based, and these use complex physics equations like partial differential equations. They are accurate but too computationally heavy. Another one is data driven approaches, which we consider as a black box like transformer and LSTM. These are accurate but require high amount of data. There is a gap, although there is some existing pins which rely on complex partial differential equation and use static weights for their load balancing. But I found there is lack of lightweight hybrid models which combine simple empirical ODEs and use GRUs with dynamic load balancing. So I will focus on this part, uh, doing some lightweight creating some lightweight hybrid models with ODs and GRUs and using dynamic load balancing. For problem statement, my goal is to estimate state of health (SOH). We define end of life as a point where SOH drop below 80%. The core challenges is to ensure it follows some physics laws, and also it we we need to estimate SOH, so that state of health with highly accurate and on some embedded hardwares. The regularizer For regularizer, I'm using simple ODEs, and these two electrochemical equations. First one is logistic model, where which is used to capture the degradation saturation over time. Another one is double exponential model. It is crucial. This is crucial to capturing the knee point, and the knee point is the moment where battery suddenly ages very fast. So these two acts as a soft constraint for our, for our hybrid models. In solution strategy, there is some proposed architecture which I'm going to use in upcoming phases. Here we going to input some data from our data set, but before that we use some Setvisky Gole filter to reduce some data noise, and then we use ICA, incremental capacity analysis, to extract the features. And for back the deep learning backbone is GRU here, which is simpler, lighter than LSTM, as it helps to deploy it some simple battery management systems or edge compatible system. And there is some optimization challenge. The hardest part of this hybrid model is the balancing the data accuracy against the physical consistency. If we tune these weights manually, it's very difficult. So my solution is I'm using adaptive weighting. In this statical method, we where the network automatically learns how much to trust the physics and the equations, the physical equations and the data during the training. And this is the equation which I will going to use in upcoming phases to found to in adapting weighting. So this is the data set description. I'm using these two distinct data sets to test the different capacities. For about NASA dataset, the data is noisy and it tests the model robustness and and can be ignore sensor noise and still see the true trends. The Calci dataset, this data shows the knee point effects. It tests the model generability to complex aging patterns. For to prove this work, I have I set up some strict benchmarking. First one is model based baseline by simple curve fitting. This is a performance floor, and another one is data driven baseline, a standard GRU, and this act as a control group to measure the specific benefit of adding physics. We can validate this model, like cross validate with this model with some techniques like loco and cross checking like training on NASA and testing on Calculate, and check if the physics informed logics help to generalize across chemistries. Another one slides, this slide shows the feasibility part. My proposed model use approximately 15,000 parameter, which is significantly smaller than transformer models. It allows us to fit within less than 128 KB flash memory and suitable for real-time use in standard microcontrollers. In summary, we address some trade-off between accurate black box models and white box models, and we propose some lightweight hybrid models using GRU and ODEs. Key contribution are the practical, not heavy PDEs, automotive, adaptive weighting will be used, and robust to noise. In upcoming phases, we are going to implement the curve fitting baselines and hybrid GRUs. And for evaluation, we conduct a ablation study to quantify the improvement improvement and test data efficiency to our models. And we are going to uh, check that models are better than standard AI, even when it reduced to training data to just to 20%. Thank you, ma'am.